All right, hey everyone. So what we're going to do in this video is shift focus a little bit to the epsilon part of the model, which is the model error. And so the model that we originally wrote is rewritten here, where our response is just some linear function of x, our predictor, and so that's this part, and then plus some kind of random error that is different for each individual in our data set. And so we're writing this error so that it's normally distributed with mean 0 and standard deviation sigma with a little sub epsilon to kind of remind us that it's the standard deviation of the errors. And so this notation just means that our errors are distributed normal, so they're normally distributed with mean 0, so that's what the first number is, so the errors are generally centered at 0, and they generally have a standard deviation sigma sub epsilon. We've talked in this model about how to estimate beta 0 and beta 1 using least squares regression. And now we're going to delve into a little bit about estimating this sigma sub epsilon, since we'll also need that parameter for when we construct confidence intervals, do hypothesis tests, and stuff like that. And so this sigma sub epsilon is kind of roughly thought as the size like of a typical residual. And so kind of this general interpretation for the estimated standard deviation of the residuals, which just has a little hat on it, is something like the size of a typical residual when using x, and so that's going to change depending on your on the context of your problem to predict y. A little bit more informally, you could think of it as kind of like how much we are typically off by when we use x to predict our response variable y. All right, so again, this is applied regression, not theoretical regression, so we're not going to really derive this estimate or really talk about why it's the best estimate for sigma hat sub epsilon. But this top numerator part, SSE, stands for sum of squared residuals, or sum of squared errors. And so that's what we've already talked about. So we've talked about how to calculate that. You'd find a residual for each observation in your data set. You'd square them all, and then you'd add them all up. And then our degrees of freedom for error on the denominator. We actually talked about this before too, so it's going to be the number of observations, n, minus the number of coefficients that are in the structure of our model. So in the mean part of the structure of the model. And so in this part, since there's two coefficients, beta naught and beta 1, because we're still just in simple linear regression, so we just have an intercept and a slope, then the degrees of freedom are just n minus 2. For the most part, we're not going to calculate that by hand, but you should be able to kind of intuitively reason that as the sum of squared residuals or sum of squared error gets larger, then our the size of a typical residual is also going to get larger, which should totally make sense. If the sum of squared residuals gets really big, then that means we're not really predicting our response that well, so the size of a typical residual would get bigger as well. But for the most part, we're just going to let R calculate this for us. And so you'll see where exactly that gets output in the your turn section working with R. In the example using batting average to predict runs, the residual standard error, or sigma hat sub epsilon, is 49.23 runs. And so this means that when we use batting average to predict teams' runs, we're kind of typically, or on average, but it's not completely on average, so we're putting it in quotes. So we're typically off by 49.23 runs. All right, so that's kind of our typical kind of error when we're using batting average to predict a team's runs across the course of an entire season. We're usually off by about 50 runs or so. In the model with OBS, what you looked at in the handout, the on-base slugging statistic as the predictor, the residual standard error is 21.41. And so we see right away that OBS is the better predictor. For runs, because the size of a typical error or typical residual is smaller. All right, so that kind of ties into this OBS really being the better predictor for a team's runs. If we use that in a model for the team's runs, then we're typically just off by about 21 runs, which is really pretty good. So if you just know a team's on-base slugging stat, but you don't know how many runs they scored that season, you could expect to be off by about 21 runs or so. And so lastly, the degrees of freedom for error in this model, using batting average to predict runs, are just going to be n minus p. But again, since we're in this simple linear regression setting, and since there's 30 teams, then our degrees of freedom for error are going to be 28. For now, that doesn't really matter. We're not really using that for anything, really. But we will end up using that when we talk more about inference, and so it'll matter a bit more in the future. And so where we're going from here is we will kind of talk about some assumptions that we need to make to fit this model, as well as some, as well as what we're going to use to end up checking those assumptions. And so this will kind of also work as a building block because we'll see that as we get into more complex models, the assumptions kind of barely change. And so we really want to get a good firm footing on them so that we could have a solid base when we get to multiple regression and start to add more predictors to our model.